Hello everyone, welcome back to our Honors Pre-Calculus videos. Today we're going to be talking about conic sections. So conic sections are basically geometric shapes that can be formed when you slice a cone. And usually it uses something called a double napped cone, which is basically when two cones are stacked like this with their vertices touching. And the reason why is because of one of the conic sections. So since there are four of them, let's start in order. The first one is called the circle, and if you've taken geometry, you should know the basics about circles. And circles are formed when you just take this slice of the cone. It is perfectly parallel to the bases, which is why it's a circle and not another shape. So the formal definition of a circle is that it's the set of all points that are a given distance away from a given point. And this given point is the center. The given distance is called the radius. Now, there are multiple ways to write the equation of a circle. In geometry, we usually talk about theorems and formulas relating to circles, but in Honors Pre-Calculus, we talk about graphing them and some of their key properties on a coordinate plane. So without further ado, let's start graphing them. We can actually use the Pythagorean theorem to derive the graphing form equation for a circle. And quickly, I'll show you how to do that. If you have the center at some point hk, and you have the radius r, that means that every point on this circle is going to be r away from hk. Now, let's assume an arbitrary point on this circle, xy. This x and y will change as the point moves along the circumference of the circle, which is why we're just using x and y, not predefined points. Y depends on x, so as x decreases as it goes this way, y increases, and so on. So that's how we would write our equation, but unlike normal function notation, we won't write y is equal to something or f of x is equal to something. Both x and y will be on the same side of the equation for this. Now, how would we use Pythagorean theorem to solve this? Well, either we can use Pythagorean theorem or the distance formula, which is derived from the Pythagorean theorem. We can say that the distance between the point xy and the point hk will be r. So we'll say r is equal to the square root of, and then you have to do the x value of the first minus the x value of the second, so x minus h. And then that squared plus y minus k, because it's the two y values, and then that squared. Now we can simplify a bit by squaring both sides, getting rid of the square root on this side, and we have our equation. Normally it's written on the opposite side. We have x minus h squared plus y minus k squared is equal to r squared. And normally h, k, and r are not variables. They're, in this case, even they're constants, but they're just placeholders because this is the general form. It's like saying ax squared plus bx plus c is the equation of a quadratic equation. A, b, and c are placeholders for any constant that can be there. Now, the main properties that a circle has are its center and radius, as shown in the diagram. And there's not much like equations to know other than the graphing form of the circle. You can also have a standard form. We'll get into standard form at the end of the video when we finish talking about all of the conic sections. But we use the standard form and completing the square to convert from standard form to the graphing form for each conic. All right. That's the first conic, circles, and unfortunately it's also the easiest conic. So moving on to the next conic, we have ellipses. In this case, ellipses are not drawn parallel to the bases, but they're at sort of an angle. So you're going to end up with something that is still circular in shape, but it doesn't have a given distance. The distance to the point changes at different locations. So in normal everyday life, we would call it an oval, but in math, we call it an ellipse. Now, ellipse also has a formal definition. Like how a circle had a formal definition, the formal definition of ellipse is it's a set of all points such that the sum of the distances from two fixed points to the curve is constant. So that was a lot. So let's break it down. Instead of having one fixed point like a circle does, which is the center, it has two. We still have a center for the ellipse, hk as well, which will be important in deriving the equation. But we have two additional fixed points. So if this is the center, we have two fixed points called foci, or that's the plural. The singular would be focus. So I'll just label them F1 and F2 for foci. And if you're given any point on this, the distance from that point to the foci, the sum of those two distances will always be the same. Here, it's the same. If I were to go here, the sum of these two distances is also the same. Okay, now let's get to the equation for an ellipse. But before we do that, we should probably talk about some of their properties. So we already talked about the foci and the center. Now we also have a few axes. On a circle, we just had radii because it's constant throughout, but here we have multiple axes to be specific. We have the major axis, which is the longer one, and the minor axis, which is the shorter one. Note that the major axis will not always be horizontal. We can have vertical ellipses as well, in which the major axis is vertical and the minor axis is horizontal. But for simplicity's sake, we'll just use a horizontal ellipse, which this is a horizontal ellipse because the major axis is horizontal. The other type, as you may imagine, is the vertical ellipse. So this is the center. We have the two foci, and these 2 points are the vertices. At the ends of the major axes, we have the two vertices. We also have co-vertices that I'll label with C1 and C2. The reason I'm not doing something like CV is because since we already have a C, but it's not C1 and C2, which is why you won't get confused between the center and the co-vertices. The co-vertices are at the ends of the minor axis. Now, we have variables and constants that we can use in the equation later on. The variables are obviously x and y. The constants are similar to r and h comma k in the circle. We have hk as the center as well. But we have a few more constants. Instead of having an r value, we have something called an a value. A is technically defined to be half the length of the major axes. In this case, that would be from one vertex to the center. And we also have a b value, which is half the distance of the minor axis. This would be the distance from one of the co-vertices to the center. But that's not all we have. We also have a c value, which is technically to be half the length of the focal length, which is the distance between the two foci. And in this case, c would be the distance from one focus to the center. So we have A, B, and C, and there's a formula that allows us to connect A, B, and C together. It's similar to the Pythagorean theorem, and for a very good reason. It's because you can derive it using the Pythagorean theorem. I won't show you how to derive it because then this video would be too long, but the equation is a squared is equal to b squared plus c squared. You might think that that looks exactly like the Pythagorean theorem, but the Pythagorean theorem uses a, b, and c, but it should really be hypotenuse squared is equal to the first leg squared plus the second leg squared, because what if you have a right triangle with x, y, and z? Then that's going to be confusing because you defined it to be a, b, and c. So in this case, we do have a right triangle. It's not obvious here, but you would use a right triangle to find that a squared is equal to b squared plus c squared. And the way you remember that is a is going to be the length of the major axis, so it's always going to be the longest segment in here, which is why it's a on this side and b squared plus c squared on the other side. Now, we also have one other thing for conic sections, eccentricity. Eccentricity is denoted with an e, and the equation for it is basically c over a. Now, for ellipses, the eccentricity will always be between 0 and 1 because c is this value while a is a larger value, so c will always be less than a. Now, when you have a circle, we didn't talk about eccentricities for circle. For a circle, it will always be 0. And the reason why is because it simply doesn't have a c value. There is no foci, so you won't have a distance between the center and the focus, which means that there's no c value, therefore you get 0 over some value, which is just 0. But you do have an eccentricity for an ellipse. There's one last thing we have to do with ellipses, and that's deriving the formula. Unlike with a circle, I won't show you actually how to derive the formula, but the formula would be, there are actually two formulas. The first one is if it's a horizontal ellipse. You have x minus h squared. So this is similar to the circle formula. Then we have plus y minus k squared. But there's a crucial difference. In this case, we have denominators to this. In the circles, we didn't have denominators, just terms like these. But in this case, we have a denominator, and it's going to be a squared and b squared. And this will be equal to 1. So this is if it's a horizontal ellipse. There's also a formula for a vertical ellipse, and as you may imagine, it's very similar except for the fact that it's x minus h squared, again, plus y minus k squared, but again, they're denominators. In this case, it'll be b squared here, and a squared here, and this is equal to 1. Now, see if you can figure out why these two formulas, how and why these two formulas are different. The reason is, let's assume it's a horizontal ellipse. A would represent the major axis, which would be horizontal in a horizontal ellipse. B would represent the minor axis, which would be vertical. In a vertical ellipse, the B value would be the minor axis, which in this case would be the horizontal axis. Because if you do have a vertical ellipse, the horizontal will be smaller, which means it's the minor, and the vertical axis would be larger. So that's why that would be a squared, and that's why the terms in the denominators are switched. So one way to remember it without remembering two equations is it's always going to be x minus h squared plus y minus k squared, again like the circle thing, and there will be denominators. The denominator of the x term will always be the horizontal axis. It will always represent it. It won't be the length of it because that would be 2a since a is half of it. We'll get into that a bit later, but it would be representing the major axis if it's horizontal, minor axis if it's vertical. So it's always going to represent the horizontal axis. The denominator of the y term will always represent the vertical axis, whether it's a horizontal ellipse or a vertical ellipse. Now, like I said, we're going to get into 2a, 2b, and 2c now. So 2a is the length of the major axis because we define a to be half the length of the major axis. Similarly, the length of the minor axis is 2b, and the distance between the foci is 2c. Now, we do have a squared is equal to b squared as a key equation to know because it's gonna come in handy when you have the value of c and b but you want to find a. You're going to need that formula. Alright, that's it for ellipses. And moving on to the next conic section, we've got hyperbolas. Hyperbolas are fun because they use up both cones in the double napped cone. It's going to be a plane that sort of intersects it here. So you've got this part up here, and you got this part down here, which is why there are always two parts to a hyperbola, and that's the entire reason we need two cones for the conic sections. So a hyperbola would generally look something like this. Obviously a bit more cleaner, but this is the general shape. And again, it has a center. Again, it has foci. Now, the definition again depends on the foci, but it's a bit of a different definition. In this case, the hyperbola is the set of all the points such that the difference of distances from the two fixed points, in this case foci, is always going to be constant. The foci would be here, and let's assume, so again, I'll label it F1 and F2. Let's assume there's a point here. This minus this, the difference of the two lengths, would be the same as, for example, if I have something all the way here, this minus this. It always would be the same. That's the definition of hyperbola. Again, these are foci. Now, if we were to draw a better representation of a hyperbola, so there's more room to draw on it. Again, we have the center, we have the two foci. I won't label that again here because they're just up here. But we also have two axes just like an ellipse. We have the transverse axis that goes through the foci and the center, and we've got the conjugate axis that goes just through the center, but is perpendicular to the transverse axis. Similar to an ellipse where the minor axis and major axis are always perpendicular to each other, in this case the two axes are perpendicular to each other, but they just have different names. This is the transverse, that's going to be the longer one, and then we have the conjugate, that's going to be the shorter one. Now, again, we have vertices that are at the end, well, not exactly end, but that intersect the curve. The vertices are the points of intersection between the curve and the transverse axis. So we've got two vertices, V1 and V2, but we don't have any co-vertices in this case. And the reason why is because there is no intersection of the curve and the conjugate axes, because that just goes in a straight line and the curve diverges on both sides and never intersects the conjugate axes. So you're not going to have any points on the curve that are also on the conjugate axis. We've got A, B, and C values again. In this case, it's transverse axis because major axis is ellipse, but it sort of corresponds to that. Make sure you know the difference, though. If you confuse between the major axis in an ellipse and a transverse axis in a hyperbola, it's fine to sort of draw parallel, but make sure you know the different names for each one. So we've got the transverse axis here, and we've got the conjugate axis here. How do we know how long the conjugate axis is going to be if there are no co-vertices at that in that line? Well, the reason why is because we know there's going to be some sort of box. That's the way it's generally seen. There's a sort of a box with the center as its center, the vertices as midpoints of its side, and then they're not called co-vertices, but I guess it's just the endpoints of the conjugate axis. It would sound better if they were called co-vertices, but they're not. So never use co-vertices with a hyperbola. They're just endpoints of the conjugate axis. So how do we determine the length of this box? Well, that's where we get B from. B is half the length, half the height, I guess, of this box, half the length of the conjugate axis, and C is going to be the distance from the focus, one of the focus points, to the center. So 2C is the distance between the foci, 2A is the length of the transverse axis, and 2B is the length of the conjugate axis. All right. Now, we said A squared is equal to B squared plus C squared in that formula. What about here? Well, C is always going to be the largest length because A will always be smaller than that. And since A is the transverse, B is the conjugate, A will be larger than B as well. So we know that C squared is equal to A squared plus B squared in this case. In that case, it was A squared is equal to B squared plus C squared. In this case, C squared is on its own. Again, think about the longest length. C is the longest length, so it's alone on its side of the equation. In an ellipse, A is the longest length, so it's alone on its side of the equation. All right. Now, we've got the eccentricity again. Eccentricity is again C over A, but we just established that C is going to be longer than A in all cases, so the eccentricity of a hyperbola will always be greater than 1. And we find the height of this box, or basically the length of the conjugate axis, using the C squared is equal to A squared plus B squared formula, because knowing C and A, we can find B, and therefore draw the box. Again, to reiterate, the foci, the center, and the vertices lie on the transverse axis, while there are no specific named points that lie in the conjugate axis other than the center, of course, because they intersect at the center. Okay, we already talked about the distances between vertices and the length of the conjugate axis. Again, it's not distances between co-vertices in this case. That's a really important point. And then finally, we talked about the distances between the foci. It's always going to be 2A, 2B, and 2C respectively. Now, we've got one more thing to talk about before we talk about the equation, and that is the asymptotes. Unlike the other conic sections, hyperbolas have asymptotes. And if I were to just erase this up here and redraw it so that we can draw the asymptotes. And I'm always just drawing these horizontal hyperbolas. Again, there can be vertical hyperbolas, and that is also pretty important. You can have a hyperbola that looks like this, and the equation would be different. The transverse axis would be vertical, and the conjugate axis would be horizontal, and so on. But for simplicity's sake, we'll just dabble with horizontal hyperbolas for now. The asymptotes are going to be lines that never touch the curve, but what the curve approaches to as it goes on forever. So we'll get into the equations for asymptotes once we talk about the equations for hyperbolas, but it's just important to know that hyperbolas have asymptotes, which is why I brought it up. Okay, let's, one more thing about asymptotes actually, they have to go through the diagonals of this box. That's actually the main purpose of this box. We have one on that side and one on this side. The purpose of this box when you're graphing a hyperbola is to be able to graph the asymptotes accurately because the box dictates where the asymptotes go. And if you think about that, you might be able to derive the equation for asymptote on your own, but I won't derive the equation for a hyperbola for you, but I'll derive the equation for an asymptote. Okay, the equation for a hyperbola, again, there are two different variants. One is if it's a horizontal and one is if it's a vertical. So we've got basically similar equations. Sorry, it's x minus h squared over a squared minus, in this case, minus y minus k squared over b squared. And this, again, is equal to 1. So in this case, it's minus instead of plus. That's the main difference. And you might think the equation for the vertical is just you swap the a and the b. It's not so simple because of this minus sign. Instead, it's y minus k squared in front of the minus sign, again, over a squared. And then we have minus x minus h squared over a squared. B squared is equal to 1. You may notice that in this case we didn't swap the a and the b. That's because we swapped the x and the y instead. That might not seem like it'll make much of a difference. It's still the same x goes to b instead of a in this case, but it makes a pretty big difference because of the minus sign. In this case, x will be before the minus sign. In this case, x will be after, indicating that there's a difference between them. So, given this, how do we find the equations for an asymptote? The equation for an asymptote, let's see. We know, let's write in point slope form because we have the point, which it goes to the center. We know that. So, if it's horizontal, we're going to write y minus y1. We'll find the y1, is equal to sum m times x minus x1. That's the point slope formula. And we can plug in some values. We know that x1 will be h because that's the center. Similarly, y1 would be k. But how would we find what m is? That's where the box comes in. I told you, if you think about the asymptotes as being the diagonals of the box, you'll be able to find the formula. Because we know that the slope of a line is just rise over run. Well, this rise is b, this run is a. Therefore, it must be b over a as the slope. But we're forgetting something. There's not just one asymptote, there's a second one as well. In this case, the rise would be negative b because you're going downwards, and the run will still be a, so there'll be a negative sign in front. How do we notate both of them in one equation? We just write a plus or minus in front of the b over a, and that represents both equations. Now let's do for the vertical. As you may imagine, it's going to be the same thing except b and a are swapped. We have plus or minus in front, and then a over b times x minus h. Okay, that's almost it for hyperbolas. One last thing I wanted to say, just a helpful reminder. so that you can memorize the equations a bit easier. Similarly with ellipses, the term underneath the x value will always represent the horizontal axis. In this case, it'll be the transverse because that'll be the horizontal one. In the other case, it'll be the conjugate because that is the horizontal one. So just like with ellipses, the term underneath dictates what axis is horizontal if it's under x and vertical if it's under y. The minus sign you might be able to remember because if it's horizontal, that means the horizontal is larger, therefore x is larger, so it should be x minus y. X should be before the minus sign. If it's vertical, the y-axis or the transverse axis is on the vertical side, so that means that the y is larger, therefore y should be before the negative sign. Okay. We have one last conic section to go, and then we have some general topics about all of the conic sections. Let's do this. The last one is the parabola. Okay, parabolas. So unlike a hyperbola, it is not using two cones, but it is pretty similar to a hyperbola. Instead of going a plane like this, there's a plane like that. And therefore, the parabola looks something like that. And because it's slanted, it does not hit the other cone and it just goes off that way, which is why it only has one part of its curve, not two. Again, there is a fancy definition for it. We don't have two foci this time, we only have one, a focus. We have the vertex. We don't have a center, we have a vertex. And then we have something called the directrix. So the parabola is a set of all points that are equidistant from the fixed point and a given line. So the given line is the directrix and the fixed point is the focus. So if I were to pick a random point on the parabola, the distance from that point to the focus is going to be the same as the distance from that point to the directrix. Parabolas are honestly, I think, the hardest conic section. Even though you're introduced to parabolas early on, this is more property related instead of just how to graph them. There is also a way to graph them that will be taught in this, but I feel that if you do it this way, it's going to be much harder than what you learned in algebra, because in algebra you just need to find a vertex and then find a few more points and then connect the curve. This case gets you more accurate curve, but it's actually a harder topic. So let's get into it. We've got the focus, we've got the center, and we've got the directrix. The distance from the vertex to the focus is called the focal length, and as you might imagine, it is c. It is length c. There is no a or b in this case, but there is an hk, which is this vertex, not the center. And there's really not much properties to go through because we don't have an a, b, and c, we just have a c. So there's no formula like a squared is equal to b squared plus c squared. Instead, we also have one more thing to know, that the distance from the vertex to the directrix is also c. This is if it's an upward facing parabola. If it's downward facing, then directrix would be above the vertex and focus would be below. It can also be on right side or left side. That technically is not a function, but neither is a circle or an ellipse, and sometimes even and also actually a hyperbola. Parabolas half the time are functions if you consider them either upward facing or downward facing, but if you're talking about left and right, sorry, I said that backwards, right and left, they're not functions. In this case, the directrix would be to the left of the vertex, and the focus would be to the right. And the leftward facing, the focus would be to the left, directrix would be to the right. Just think, whatever direction the parabola is opening in, the focus is also in that direction when compared to the vertex. And now we get to the fun part, which is the equation. The equation is, again, there are two. One is if it's vertical, and the second is if it's horizontal. Let's start with the vertical first, and that seems out of order, but the reason is because even though it's a vertical parabola, the directrix is horizontal, which is why we're starting with that. It's still counted as technically an axis as horizontal or something. Therefore, we are starting with that. We have y minus k is equal to 1 over 4c times x minus h squared, and that's the equation for a parabola. We've got x squared, which is why it's a parabola. We don't have y squared. That's a difference from other conic sections. Only one of the terms is squared. We'll talk about that a bit later near the end of the video. And this 1 over 4c is important because how to graph a parabola would include this a little bit, and we'll talk about that at the end of this parabola section. But first, let's talk about the horizontal parabolas in which the directrices are vertical. We have x minus h in this case is equal to 1 over 4c times y minus k squared. In this case, the y term is squared, so you're basically swapping the positions of x minus h and y minus k to get this. Again, hk is the vertex in both cases. C is the focal length. 4c we'll get to very quickly. I'm just going to get rid of the other parabolas that we drew, and now let's get into how to graph a parabola. So you always have to start by graphing the vertex. Let's say it's h comma k. We get some vertex here. Then we have to graph the focus. Let's assume it's an upward facing parabola. Therefore, the focus must be above the vertex. So let's just say it's that much. The only reason I'm doing a small amount is because of what comes next. So if this is C, the directrix must also be that length below the vertex. So that's the directrix. And finally, we want to actually graph the parabola itself. You might just find some point and then graph it like this, but that's not how you're actually supposed to graph a parabola in algebraic calculus. What you're supposed to do is when you get C, the width of the parabola at the point of the focus will be 4c. So it'll be 2c on either side. You go 2c that way, you go 2c that way, and then you get 2 more points on the parabola. So now we can erase this 2c and this c, and we'll get a parabola once we connect these points. Again, since it's on a screen, it's not going to be the best parabola you can draw. Make sure that it should all be connected. That's how you graph a parabola using this equation. Again, it's a bit more difficult than what you do in algebra because that gives you a vertex form, for example. In this case, instead of there being an a term in the vertex form, it's going to be 1 over 4c, and you use that 4c to find the focal width. All right. That's basically it for all of the conic sections we need to know. If you were to take a college level course, it'll go more in depth into each one, talking about how you can find planets' orbits using ellipses, or even some comets' orbits using parabolas, etc. But this is just a high school honors pre-calculus lesson, which is why we're just going surface level on each one. But there's one last thing we need to do, and that is to find the standard form of conic section. We also want to revisit eccentricity at the end, but first let's talk about standard form. There will always be some ax squared plus by squared, and technically it continues to plus cx plus dy plus e and so on is equal to 0. So you just get ... That would always be the standard form for any conic section. But you can use completing the square to find the graphing form, because let's say if you have 2x squared plus 2y squared plus 4x plus 16 is equal to 0, you can divide everything by 2 first. You get x squared plus y squared plus 2x plus 8 is equal to 0. So you can complete the square. You get x squared plus 2x. So if you do that here, x squared plus 2x, you can add 1 because that's how you complete the square. And then again, it's just a y squared by itself. You move the 16 to the other, the 8 to the other side. Once you divide by 2, it becomes 8, so it becomes negative 8. You add 1, so it becomes negative 7 instead of negative 8. This technically is not a conic section because you have a negative value, but assuming it did come up to a conic section, you would say this is a circle because it's in the form of a circle some radius. Again, this was a bad example because you get a negative value, but just imagine that if you do get a positive value on the other side, it will be a circle. However, we don't have to complete the square if we just want to know what type of conic it is. If we want to find the graphing form, yes, we do. We absolutely do need to complete the square, but just to find out what type of conic it is, there's actually a set of rules. First, if it's a circle, a will always be equal to b. In this example, we just saw we got 2x squared plus 2y squared. It could also be just x squared and y squared. A just has to equal b. If it is an ellipse, a is not equal to b, and the signs are the same. So you have like 2x squared plus 3y squared. The reason why is because we do have a plus sign in the ellipse equation, but there are different denominators, which means there are different coefficients, which means a should not be equal to b. Third is for hyperbola, a is not equal to b, and there are different signs. So I'm just going to write same here and diff here to show that they're the same signs, different signs. The reason why it's different is because there's a negative sign in the hyperbola equation, which is why one should be positive, one should be negative. Finally, we have a parabola. Just either a or b is equal to 0. One of them is equal to 0, which means that you only have one square term, which fits with their equation for parabola because we only have one, either x squared or y squared at the same time. You can't have both, which is why a or b equals 0. That's the rules for the standard form. That's just if you want to convert that's not if you want to convert into graphing form, but that's if you want to find out what type of conic it is. And I know this video is really long, but there's just one thing we need to talk about again, and that's eccentricity. We went over it for some conics, but I just want to remind you, for a circle, eccentricity will be 0 because there is no c value. For ellipse, eccentricity will be actually between 0 and 1, but I'm just going to write less than 1. It should be between 0 and 1. But since you can't really have negative eccentricity because it's c over a, none of them can be negative, I'm just going to write less than 1. The third one is for parabola, actually. We're going out of order a bit, but I can always change the fourth one to a parabola instead. E is equal to 1. Parabolas have an eccentricity of 1 always. And finally, for a hyperbola, e is greater than 1. It can be any value greater than 1 because c will be greater than a. Because, remember, the equation for eccentricity is c over a, which is why all of these rules work. That seems to be about it for our conic sections lesson, and we'll see you next time. Good luck for honors pre-calc.